How are complex robot arm motions planned and executed? Robots are commonly mounted inside enclosures or environments that restrict their movement, and their tasks are rarely as simple as picking up simple objects from above. So how can we reliably plan complex robot arm motions? One excellent answer is MoveIt. MoveIt is a powerful and widely used framework that allows robots to plan paths between 2 points, while avoiding collisions, respecting joint velocity limits, and following robot constraints. In this video, we'll work through the official tutorials from the MoveIt website step by step, with a particular focus on the Pick and Place with MoveIt Task Constructor tutorial at the end. Timestamps are in the description, so let's start at the beginning with getting started. This is the tutorials page from the MoveIt website. You can see all of the tutorials listed at the bottom here. We're going to begin with getting started. So this tutorial runs through how to install ROS2 and Colcon. So I'm using my Ubuntu laptop, which already has Jazzy installed, but you can feel free to follow these instructions to install ROS2 for yourself. I'll be following the instructions from underneath the ROS2 installation onwards. So here I am, remote desktop into my Ubuntu laptop. And what I can do from here is I can use the command line to install MoveIt. So first, it will be making sure I've sourced the ROS2 installation. So that's source opt ros jazzy setup.bash. Now, if you're using a different flavor of Jazzy, you might have to adapt these instructions, and I'll point out where the changes are. This is the first one. You need to change the ROS2 version name. Once that's done, you need to make sure that the ROSDEP package is installed, which is written in Python and will allow you to install a lot of the dependencies automatically. So ROSDEP as a tool will look through a ROS package and find all the packages, the system packages that need to be installed for that package. Then we need to complete the ROSDEP installation, which initializes it and updates it to make sure it's got the latest packages that are available. So with this last step, we've initialized ROSDEP and updated it, and also done a complete system update. The next step installs an extension to Colcon, which is ROS's build tool, to enable mix-ins. Mix-ins are a way of specifying multiple command line arguments at the same time using one global keyword. So for instance, you might specify a release keyword or a debug keyword, each of which defines a bunch of command line arguments. And the final part of the installation is to install the VCS tool. That's all of our dependencies installed. The next step is to create our workspace. This is the standard command to create a workspace with a source folder. I've already got this workspace, so I'm going to check out everything into a second workspace called MoveIt2. Next, we're going to cd into that, and then clone the branch that we want of the MoveIt2 tutorials package. There's two options as I'm recording this. There's either Humble or there's main, and main corresponds to Jazzy, so that's what I want for my Jazzy installation. With the checkout complete, we can now use the VCS tool that we downloaded just before to automatically clone all of the supporting repositories. So using this, we can just wait for the clone to complete. And that's all of the source code checked out. Now there's a few steps to make sure that all the dependencies for the packages are installed. So first we want to make sure there's no existing package for MoveIt on the system. And there you can see that none of the packages are installed, so none removed. Then we can use this command to search everything under the source directory and install all of the dependencies required. This is a pretty standard step to do for a new ROS2 package. It doesn't necessarily install any new dependencies, but you can make sure that your system is set up if necessary. Finally, we can go up one folder and we can execute the build command. Now the tutorials say to use the release keyword, but I'd recommend using the debug, at least while you're doing the tutorials. You can use release if you're using a production version of MoveIt, but to avoid having to compile it again in debug mode later, we're going to use the debug keyword now. And that's especially important because compiling this workspace takes over an hour, at least for me. I'm going to cancel this build command because I've already run it in my other workspace, which I'll be working from next. Now, if you're struggling to compile because your system doesn't have enough resources, some of these packages can take 16 gigabytes of RAM or more. You can use a different build command which is specified by the MoveIt tutorials, which will reduce the number of packages that can be built at the same time, and using the executor of sequential will only build one package at a time to make sure that you can build it properly. So I can execute the build command in this workspace instead, and it will work through all the packages that have already been compiled and check there aren't any changes, and if there are changes, compile them. But it should completely run through without making any changes. You can see here it's running for about 15 seconds, even though there's no updates to make. So even compiling a workspace that you've already compiled can take some time. So as you can see from the standard output I've got here, I eventually gave up letting it do a full build of my workspace that hadn't been changed, because it was running for about 13 minutes and still going 52 packages out of 70. So instead of letting that finish, which does take a long time, we can move on to the next step, which is to source the workspace. Once you've sourced install setup.bash, you're ready to use it. But there is an extra thing you can do if you want to make things a bit easier in future, which is to add it to your bash RC. So if you move into your home directory and then edit your bash RC with whatever tool you prefer, I prefer Vim, then make sure that these lines exist, source optros jazzy setup.bash, and source your MoveIt workspace install setup.bash, and then any new terminal that you open will automatically source your MoveIt workspace. Now that's done, we can actually run the demo application. So running the supplied demo.launch.py will bring us to this screen. Now the tutorial says that you need to do some initial setup. I found a lot of it is unnecessary, but I will show you some of the options that need to be changed anyway. So tutorial says that at this point you'll see an empty world in RViz. So as I already get the robot arm, I will skip the importing the robot arm step, as I assume it will be the same for you. But a few things to check before you carry on. First, the fixed frame is set to base link. Then I like to adjust my windows a bit. I don't need all of this space, and I don't need this description, so I can see a bit more of the RViz topics available. So collapsing these down so that we can get to motion planning. I want to make sure that the robot description is set to robot description. The planning scene topic is set to monitored planning scene. We expand planned path, then the trajectory topic should be display planned path. And finally, if we look at the planning request dropdown, we should see the planning group is set to manipulator, not gripper. So as soon as you do that, you find that the robot is highlighted and now it has this orb on it. So you can drag this and move the robot around. Or rather, what you're moving around is the end state of the robot. So from the current state to the end state is what we're seeing in this visualization. A few more things before we actually start planning and executing movements. There are some visualizations that we can turn on and off. Under the scene robot tree, we've got the show robot visual. Under the planned path tree, we've got show robot visual. Under the planned path tree, we have the show robot visual. And under planning request, we have the query start state and query goal state. If we enable the query start state, we'll get the start state of the robot in green that we can move around. But given that by default, it will plan from the current state to the end state, I'm going to leave that off for now. So the next step is to actually start planning movements. So the tutorial says to untick this scene robot, show robot visual, and under planning request, tick the query start state so that the green robot is available. Now you can move these around and you can begin to plan paths between them. You can see it takes just under a second to plan that path, and it's creating a smooth motion from the green to the orange. So you can now start to drag around these visuals and plan and execute paths. Now the green is exactly aligned with the robot. We can plan and execute a motion from the start to the end. And the front robot arm here is the planned motion, and the other robot arm is the executed motion. And of course, as this is a simulated arm, it looks exactly the same, but in real life, you might see some differences. And now that the robot's completed its motion, the start state has moved to the goal state. The next step is to try and move the robot into collision. So under planning request, untick query goal state. You should only have the green arm available. Now you can try and move this around and see if you can make it collide with itself. And if you can, I'll be impressed because I couldn't. It will simply stop motion once it reaches a point it can't move anymore. And what you can do is turn off collision aware IK. And I found that even if I did that, it still fails to move. It will just jump past the part where it's not able to move. So I'm not sure what the tutorial is showing here. I couldn't get it working myself, but given that it will plan paths and avoid collisions when you're actually running the code, I was fine just skipping past this step. You can also see what happens when you try to move the arm outside of where the arm can reach. So when it's fully stretched out, what happens? It just snaps to the furthest position it's able to get to. And again, there it is. Now from the planning tab, we can go to this joints tab. This has extra options to be able to set specific joint angles and also to explore the null space. So this is when the robot has more than 6 joints, so it can actually use multiple configurations to reach the same point in space. You can start to move this slider and see the robot. It's very subtle, but you can see the elbow in the middle here is just rotating while the gripper stays in exactly the same space. That's because these different sets of joint angles all result in the same tool position, so you can try and explore the null space. So now let's turn the goal state back on. We're going to move this over here, and then back in the planning tab, we're going to click plan. You can see it's planned a successful motion from the green to the orange. But if we expand the planned path menu, we can tick the show trail checkbox here. Now you can see the motion as it's moving along the path. So the robot arm position at each point in the trajectory is shown. So it becomes a bit of a blur, but it is a useful visualization of what the robot arm is planning to do. Next, we can select the planning and then enable the trajectory slider button. From here, we can move the robot arm along its path. So from the beginning, we can move along and see it move along the path, including making the trail as it goes. That means that you can inspect all along this path what point the robot expects to be in. Next, for the Cartesian planner, we're going to click the Use Cartesian Path button. And then if we click a plan, so I've just opened my RViz back up again because when I clicked plan last time, it crashed trying to plan a Cartesian path. So we'll try again. We're going to click Use Cartesian Path. And when we click plan, what I'm expecting is for it to fail to plan after it reaches the plan time timeout of 5 seconds. Actually, what's happened is it successfully planned a path. So you can see here that it's planned a straight line path in Cartesian space, meaning if you held a paper up against this line, it would draw a straight line across it. And you can see from the visualization as well that the joint angles change in order to keep the tip of the tool in exactly the same line, while the rest of the robot compensates for that motion so that it keeps a straight line. Let's turn off Cartesian path because it is more difficult for the robot to plan. And we can see here that the velocity scaling and acceleration scaling are set to 0.1. That means they're running at 10% of the maximum that the robot can achieve. So we could move the robot faster, twice as fast, and accelerate twice as fast by typing in 0.2 here. And now our plan. And you can see the robot is moving visibly faster. So you can either change these scale factors within RViz itself, or you can change the configuration file to make it more permanent so that when the robot launches, it has different parameters available. Next, we're going to open up the RViz Visual Tools GUI. So if you open Panels and select Add New Panel, and then under RViz Visual Tools, we get this RViz Visual Tools GUI. Now it's very small, it's only a few buttons, but we will be using these in the future tutorials to actually make the robot move along the steps of a task, for example. Finally, and this isn't necessary, but it is really useful for being able to run the same workspace in future, we can actually save our configuration. If you click Save Config As, and again, my RViz crashed when I tried to do that. So again, we can save config as, place it somewhere within the directory. I've already saved this one earlier, hello MoveIt. So I'll be reusing this one for the next tutorial. You can save this config here, and then in the future, you can launch a different command line parameter that I'll show you in just a So now instead of just running demo.launch.py, we can add another argument, which is RViz config, and then your RViz config. So in my case, it was hello MoveIt.RViz. Now, if I run that, it will launch exactly the same parameters, all the same checkboxes as I had configured last time. And that's it for the MoveIt QuickStart in RViz. So the pre-built demo with all of the interactions that you can perform using RViz. Next is to actually start coding. So we're going to create a beginner project that uses MoveIt and just performs a simple motion. So here I am in VS Code on the laptop. First thing I'm going to do is use Control-K-O to open up my workspace. So workspace MoveIt, click open. I'll zoom in a little more. I'm going to change into the source directory and then execute the command to generate a ROS2 package. This will create a new package within our directory, which is called Hello MoveIt. Now we can take a look at the package.xml, which contains some of the basic information, the metadata about the package. And you can feel free to fill these in for yourself if you want. As it's a tutorial that I'm not planning to keep, I won't update it. There's a CMake lists, which has also been generated, which describes how to compile the package, and a source file, hellomoveit.cpp, which just has an empty main function in. There's also an include directory that's been created, but as there's no files inside it, that's not useful to us yet. So from here, we should be able to build our workspace. Remember to mix in debug. And then it's just got to where it got to before, so I'm going to let it continue as we start to code this application. So it's not distracting, I'll open up a separate terminal. What I recommend doing for these tutorial steps is to try and write the code yourself using the tutorial as a guide. Write it as if you're writing it from your own blank project and you're trying to understand how it works. Now, I won't be doing that right now because I want to show you how it works and describe it. And writing the code doesn't help with that, but for your own version, try and write it yourself. The first thing I'm going to do is copy this code in. So we can see there's a few includes. The main function is still here. And what it's doing is initializing RCL-CPP, which is a C++ library that wraps ROS2. And it creates a node called Hello MoveIt. There's a special function which you need to use with MoveIt, automatically declare parameters from overrides, and then it creates a logger. Finally, it's got a blank space for some code, and then it shuts down at the end and returns 0. So this is the kind of boilerplate code that you can use in pretty much every MoveIt project that you need to use. Now from here, the tutorial recommends building and running the project just to see it successfully run and produce nothing. As my workspace is still building, I'm going to continue on to the next step. So I've pasted this code in. I can delete this comment now, it's no longer necessary. And what we're doing is using a move group interface. So what this does is imports it so that we only need to use the keyword move group interface. And then we're constructing it. And importantly, we're constructing it with this string, the manipulator. We're trying to move the manipulator. That's what we're focused on moving, not the gripper, not a particular joint of the arm. We're moving the manipulator. We're then creating a target pose. Now, if you've not seen this square brackets, curly brackets syntax before, what this is doing is create a closure function. Essentially, it captures some data from the surrounding area. In this case, the brackets are empty, so it captures nothing. It defines the code to run as part of that function, and then these brackets mean execute immediately. So what's going to happen is we create a function which generates a pose, and then we execute it immediately and store it in this target pose variable. Our target pose will have an X, Y, and Z position, which you'll be used to. Now the orientation is a quaternion, which is 4 values used to specify a rotation in 3D space. In this case, we need the W value to be 1, and we're going to leave the X, Y, and Z values as 0, which means no rotation. That's a 0 rotation. So that's our pose constructed, and then we can use it to set the target pose on our move group interface. All of this code is constructing an interface with MoveIt that moves the manipulator to this pose. The next step is to create a plan to that target pose. So again, we're using a closure. We're capturing the move group interface this time, and then we're creating a plan object called message. Then we're checking if we can plan a route to that message, and then we're returning a pair of OK, whether we planned it successfully or not, and the plan itself, which is written as message. They're stored as success and plan, automatically unpacked. So now we can see if success, then we're going to execute that plan. So we've planned the path to our target pose, and now we're executing that plan. If it's not successful planning a route to that pose, then we're going to log that as an error, and then we're back to our original code, which shuts down. Now that my workspace has successfully built, we can compile this function and try running it. So what I'm going to do is run the demo script. That's again going to launch RViz. And with RViz running, we can now run our new package. Remember to source your workspace. Then we're going to ROS2 run, hello MoveIt, hello MoveIt. And you can see in the logs here, it's ready to take commands. It accepted the planning request, completed the planning request, and executed that request. Now, if we look back at RViz, we can see the robot arm in motion from the beginning pose to the target pose that we just set in code. And there we have it. That's our first C++ MoveIt project complete. We've managed to programmatically use MoveIt to move our robot arm to a specific target pose. Next, we're going to add some code to our Hello MoveIt project, which helps us to visualize what's happening with the robot. First, we can open package.xml, and we're going to add a new dependency. Once that's done, we can open our CMake lists, and we want to compile and link to our new dependency. So for that, we've got a few lines to add. First, we need to find the package. Then in this amend target dependencies, we need to add a line for MoveIt visual tools. So we can copy this and just put it in speech marks. Then we can add a new include to our source file. And finally, we can rebuild. And if it successfully builds this time, we know we've included the new dependency on MoveIt visual tools. Now, it was successful, but in the future, if you want to skip compiling all the other packages, you can use the keyword packages select hello MoveIt, and that will only compile hello MoveIt. See, that was much quicker. Now we have a new header that we need to include, the thread header. Then we're going to add an executor. Just after our logger, just before our move group interface, we're going to use this code. So because of how the MoveIt visual tools interacts with the node, we need to use an executor in order to run it. So we construct an executor, add our current node to it, and then spin it inside a thread. And now the visual tools will be able to interact with it and block it if necessary, like we're waiting for a button push from the visual tools. All we need to do now is make sure at the end to join the thread. So what we've done is told it to shut down and then wait for it to finish shutting down using this join function. Next, in this gap after the move group interface initialization, we're going to paste this code in, although you'll write it for yourself. So this creates the visual tools using our current node, our ROS2 node, baselink, which is the baselink of the robot that the visual tools are handling, the RViz marker topic, which is a static constant, and our robot model, which we can get from our interface. Then we're deleting all the markers in case anything was there before, and loading remote control so that the buttons can affect the running of the code. Then we're going to create a few more closures. These have different functions, and they're named draw title, prompt, and draw trajectory toolpath. So this first one will take any text and draw it onto the screen 1 meter above the base link, and that's pretty key. But broadly, we're placing a label with no rotation 1 meter above the base of the robot, and then we're setting the text inside that label to be white and extra large and contain the text that's passed into the function. Now we can call draw title anywhere else in the code in order to draw some text above the robot. In a similar way, we can prompt the user for some input with auto text, and the final closure will look up the joint model group for the manipulator, and given a trajectory, we'll publish that trajectory line. So basically, given a trajectory, starting from the manipulator where it is, draw the line. So that's a great way of visualizing what's planned for the robot or what it's currently executing. We can see what's going on better and debug our code. With the functions defined, we can now start to visualize the parts of the code that we'd written before. First, we're going to prompt the user to press next before actually beginning planning. Now, this key line here is pretty important. When I was coding this for myself, I missed this out. What this does is it updates the visual tools. All the changes that you've told it to do, it will update them all in one batch, but only when you use this trigger function. Then it does the plan that's already here, so we can delete this. Then we can replace the plan execution step to also draw the trajectory toolpath, do a trigger so that it's updated, prompt the user to press next, then draw that we're executing. So this means the state of the robot will be updated as it's performing its tasks. Finally, we execute the plan. Now there's also some extra error handling we can do. So if the planning fails, then we can draw a title above the robot saying the planning failed. Now that the code is complete, we can again build it and run it exactly the same as before. So we're going to restart MoveIt. We're going to relaunch RViz to make sure that the robot is in the home position, otherwise it's not doing any movement at all. And there's the robot. Now if we run our Hello MoveIt code, we can see it's waiting to continue, press next. So we'll click next. Now it says it's planning. And you can see it's doing its trajectory toolpath that's drawn in. And we're waiting to continue again. So press next again to execute. Now it's executing and our label is finally not hidden behind the robot arm and we can see it moving around. So these are the tools you can use to debug your robot while it's moving. Using graphical tools to debug is incredibly powerful. It's very easy to get stuck into just debugging using the command line or using the IDE, but having buttons to prompt things to happen, stepping through step by step, and drawing things onto a screen is so powerful. I really recommend learning and using it, and not just in robotics development, but in all software development. If you can build a GUI for a long-running tool, it will probably save you time in the long run. And that's our RViz visualization tutorial complete. The next tutorial is planning around objects. So what we're doing in this tutorial is creating an object and letting MoveIt know it exists so that when we plan motions, it will plan around the box. This is one of the most powerful uses of MoveIt. So we're going to start by adding this extra include. Then we're going to update our target pose. We've now got a value on the Y orientation and on the W orientation. And our X, Y, and Z positions have all changed as well. That's because we're creating a box that will get in the way of the robot and we're making sure that our target pose is on the other side of the box. When I first wrote this, I didn't update the target pose. The robot arm planned a path without going anywhere near the box, and I was a bit confused why the tutorial had included it. Next, we're going to create the collision object. So I'm going to paste this code directly in. So what we're doing is getting the frame ID from the move group interface, which should be the base link of the robot, so that when we create an object, it's referenced from the base of the robot, not from the gripper being in a random location. We're going to create a collision object with that frame ID, call it box1. We're creating a 3-dimensional box, hence the resize 3, and we're setting its box X, Y, and Z to these dimensions. Then we also need to set its pose. We've told MoveIt what the size of the box is, but not where in space it is. So again, setting 1 on this W makes it a unit rotation, meaning no rotation. And we set these X, Y, and Z coordinates so it's beside the robot. Then we're going to push it onto our list of primitives, meaning we can add multiple objects at the same time. We're going to push the pose back so that it's matching that box to say that this box is at this position. And then we're adding it to the scene. We're not modifying it or doing any other operations that are available, append, move, etc. Then we're returning the collision object. And again, this is a closure that's immediately called, so the result is saved in this collision object variable. The next step is to add this collision object we've just created into the scene. So we're creating a planning scene interface and applying a collision object. So we're saying this box is something the robot can collide with, so it should plan to avoid collisions with the robot. Now our code is ready, we can rebuild it. And when we launch RViz, we're going to use a different RViz file. So let's close this. We'll paste this in. We're going to use the Canova hello MoveIt just to save us having to set the workspace up again. Here we are, our RViz is launched and our node is ready to run. So let's run this. And once we run it, our box appears in the space. Now we want to move the robot arm to beside the box here. So as you'll remember, the next buttons will plan a motion, and it's starting to plan, and it's got a trajectory that goes around the box. And see, the elbow here is avoiding the box. So at no point does the robot arm hit the box anywhere along the arm. Then we're going to execute that motion. So you can imagine you can build up an enclosure of 3D objects that the arm has to avoid, and it will make sure at no point does any part of the arm hit any of the collision objects. Here we are, it's completely avoided the box and picked up an object on the other side of it. And that's our Hello MoveIt project complete. We've seen how to set a target pose for the robot. We've seen how to add visualizations into RViz so that we can understand what's going on better. And we've seen how to add collision objects to the scene that the robot can plan around to avoid knocking into anything. The next step is the most complicated yet, which is creating a more complicated motion for the robot using the MoveIt Task Constructor. This is the Pick and Place with MoveIt Task Constructor tutorial. Now the MoveIt Task Constructor is actually an optional add-on for MoveIt. So if you're trying to use it in your production projects, don't forget to enable it. There's a line in the launch file that you can do. If you want to see how to do that, you can check the tutorial, or you can check my blog post linked in the description, which has more information about how to enable that in your launch file. But what's trickier to understand here is the basic concepts. So we're not just making the robot move now, we're trying to do more complex motions, which require more planning. So the top level planning problem is called a task. All subproblems of that task are called stages. And the idea is that by specifying different problem parts, we can create a more complex motion and do more complex actions. There's 3 possible stages, or I would say there's 3 main stages, which are generators, propagators, and connectors. Now, you're welcome to read through the tutorial for this, but I think it's easier to understand if you go through the design that's going to be built step by step to see how it builds up and how each stage contributes to that design. So briefly, we can look at generators and see that they generate something, a pose or a state, and pass it to neighboring stages. So here's a diagram to show it. It creates data and passes it upwards or downwards. Propagators receive the result of a neighbor stage and then do something to it. They produce new data and pass that. So if data comes from above, it processes it and passes it out the bottom. From the bottom, it can process it and pass it above. Connectors don't propagate results, but bridge the gap between results. So they take data from the bottom and the top and try to meet it in the middle. Now these will make more sense as we see them in context of an example, which is trying to pick up an object. Actually, we'll build the entire design for moving from home to pick up an object, to placing the object and moving back home again. But we'll start with the pickup stage. We're going to define a series of stages for how to pick up an object from the current position. So to define our series of stages for picking an object, we'll use this draw.io, and we're going to start by generating a grasp pose. So that's going to be a generating stage. What this means is for a given object, we want to generate a valid grasp around it. Maybe that could be beside the object, it could be coming down from on top of the object, but that's going to generate the grasp. However, we don't want to move directly to the object. We want to move to slightly off the object to make sure we can reach it successfully, and then move to the grasp pose. So before the grasp pose, we need another stage. I'm going to use a parallelogram to represent it, and it's going to be the approach pose. Now the approach pose is based on the grasp pose, so it needs to know what the grasp pose is in order to move it slightly off. So it's going to take data from the grasp pose. However, when we're executing it, the execution order is from top to bottom. So the robot is first going to move to the approach pose, Then it's going to move to the grass pose. But in order to plan the motion, we need to know the grass pose in order to create the approach pose. And that's why MoveIt talks about data flowing in two directions. We have a generator that's passing data upwards. Once the gripper is around the object, we actually want to close the gripper, which is exactly the same pose as the grass pose, but with the gripper closed instead of open. Therefore, we're going to need another propagator stage, except with the grass pose passed into it, so that it can modify only the gripper position. So now we've got our gripper closed around the object, we want to lift it up so that we can do something with it and it's not going to bash into anything on the table it's on. That is again going to be a propagator. That's going to take the pose from the closed gripper and it's going to lift it directly up from wherever it is. So again, we need to pass the data down. So now our execution order will begin by approaching the object, then we'll move to grasp it, then we'll close the gripper around it, and then we'll lift the object up again. Now that's pretty much it for the steps of a pick, but we need to do some extra steps in order to make MoveIt understand how to do these steps. Firstly, a grass pose is specified as a pose for the tool, but that's not what the robot arm moves to. We need to convert it to a set of joint angles. That's a process known as inverse kinematics. Now there's a simple way to do that, and that's by creating a wrapper stage that goes around the generate grass pose. So let's take this box, and we're going to place the grass pose within it. So there we have our generator with our wrapper that computes the inverse kinematics. Now the other stages also need to be able to compute inverse kinematics, but we only need to specify it for the generator stage for the other propagators to understand how to do it as well. It's passed along by MoveIt. Next is a couple of kind of housekeeping stages. So they just tell MoveIt that the scene has been updated. So they're modify planning scenes. And that actually counts as a propagator, not because they need a pose from the robot arm, but because the data needs to pass through the propagator stage. The first enables collisions, and that just tells MoveIt that for the object we're trying to pick up, the collisions need to be enabled so that the gripper can actually touch it. So we're going to enable collisions. Then once the gripper is closed, we need to tell MoveIt that the object is attached to the gripper, meaning when the gripper is moved, it will move the object around so that it can track the object's position. Now we don't need the pose in order to enable collisions, but we do need to pass that data through to the closed gripper because that's necessary for the gripper to be able to calculate. And that is a complete set of stages that will do a pick motion. Now, what we can do here is wrap them in a serial container. By wrapping it in a serial container, we're bundling these stages together into one named subtask, as it were. So we can now use this within a larger task or within multiple different tasks, or we can execute this by itself as its own task. What we can also do to avoid complicating our diagram further is just collapse this down to a pick object stage. Now that our pick object is defined, it's your turn to try and define the place object set of stages. Instead of generating a grass pose, generate a fixed pose, and otherwise try and insert the wrapper stages so that we have a place object subroutine similar to the pick object subroutine. As it is, I'm going to simply have a place object. Now what we want to do is use these two subtasks in order to define the full motion from home to pick to place to home again. This is where our last connector type comes in. In order to move from pick object to place object, we need to connect them together, meaning we need to resolve a path that goes from the final stage of the pick object to the first stage of the place object. And we can do that with a connect stage, which is the only type of connector stage. Now again, notice the flow of data here. In order to plan a path from pick object to place object, we need to know the start and the end points, which means data is coming in from above and up from below. And that's why our connector stage has down from above and up from below. So with this alone, we can move from a pick to a place, and it will plan a path that goes from one to the other. Now our diagram is actually going to go from the current pose to the pick object. So what we need to do is write current pose, and that's a standard generator within MoveIt. It says get the current position of the robot in order to go to the next stage. So if we want to go from the current pose to pick object, we again need a connector. So here our current pose feeds into the connector and our pick object feeds into the connector. So from current pose, go to the pick object. However, our pick object assumes that the gripper is already open, and that's likely what we want to be the case. So instead, we're going to add another stage, and it will be a propagator stage. Just as pick object has a propagator stage to close the gripper, we need a propagator stage to open the gripper. So from wherever we are, make sure the gripper is open, then move to the pick, which will be the approach pose. Finally, from place object, we need to go home. That's actually a propagator stage. Instead of move relative, it's moved to a fixed position, which is the home position. So this will be our move home. And again, we need to connect it. So from place object to move, and from move home to move. And that's it. That's our full design, and that's what we're about to implement in code by copying and pasting chunks of code. So we're back on the Ubuntu machine, and the first thing we need to do is check out the MoveIt Task Constructor, because as I said before, it's an optional add-on. So we're going to go into our workspace, and I'm using my fresh workspace that doesn't have it in yet. We're going to git clone -b, and again, it's either humble or main. So I'm going to use main, and then MoveIt Task Constructor. Now here it says that I've already got it checked out, so it was likely imported automatically by the tutorial's listed repositories, rather than needing to do it again. Now the tutorial says to install extra dependencies, but as the repository already existed, we have the dependencies already, so we can skip this step. So what we can now do is use some of the visualizations that are available. So to run the pick place demo, we're first going to run the demo launch py. And then in a separate terminal, remember to source the workspace if you haven't, unless you've set it up to run automatically. In a separate workspace, we can run the run.launch.py with one of the examples. So I'll use the pick place demo. So here we can see RViz. We've spawned an object here, which is a flat base with a cylinder on it. And I'll expand this out, and you can see the motion planning tasks here. So it's got a bunch of different stages. It's got the pick object, it's got a connector, it's got the place object, and we can actually run these all in a row to see it work. And there we have it. It just picked up an object and placed it back down again. Now, if we want to get to this menu, we need to do a panels, add new panel, and open the constructor visualization motion planning tasks. That's because it is its own panel as an add-on to MoveIt. And it shows us this list of tasks that are available, and it can see the number of paths that have been planned that are possible. So from our task list, we can click on any of the tasks, and on the right, click this number. And it will show us the different visualizations. So you can see that from here, our gripper is closed, and if we click open hand and click the number 1, it opens, and you can see the visualization here. You can see it more clearly if we click on the close hand, because this pose is around the object. So if we click 1, the visualization shows the robot having already picked up the object. If we click the overall pick place task and run it, you can see it actually working. And if we run all the different versions, you can see differences in how it's planned. See, there's a double spin on this number 8 that isn't available on number 10. Let's run that again. It does a somersault over, and then this one, it moves off and then does a somersault back again. So that's it working. Now let's take a look at how we can use this in code. We'll build up the diagram that we built using draw.io, except using code. First, from our source directory, we'll use our package create command again. We're going to create an MTC node with node name MTC tutorial. And here it is. So what I'll do is I'll go through and explain what's going on in this code. First, we've got a logger and we've got a new namespace, which is the MoveIt Task Constructor. By labeling this as MTC, it gives us much easier access to everything. So we're creating a class called the MTC task node. It's got a few helper methods to make things a bit easier for when we get more complex motions, including doTask and setup planning scene, which will be our initialization of the planning scene. Let's collapse this down and move on. Our constructor just creates a node called MTC node. Our function to get the node base interface just returns the underlying node's base interface, so we can skip this. Now our planning scene has a bit more to it. We saw this in the last tutorial of planning around objects, where we create an object, except this time it's an object to be picked up rather than an object to be avoided. So we still apply it as a collision object, but it's a bit simpler, and it's a cylinder instead of a box, so it's got different dimensions. But I'll skim over this because it's not too much more information. Next, our doTask function that's actually going to plan and execute the motion. We create a task, which is its own function that is defined separately. Then we initialize it, then we try and plan for 5 seconds. And if we didn't manage to, we log as task planning failed and return. If we are successful, then we can publish the first solution that we found, because it could plan multiple solutions, so we publish just the first one, and then we execute it. So all this function does is creates a task, plans the task, executes the task, with logging if it fails. So we can collapse that down, and then within doTask, we are creating the task. Now this is the function where all of the stages from that draw.io diagram are built. So there's a bit of boilerplate code. We create a task, we set a demo task stage name, and load the robot model so that it can understand how to move the robot around. We also set a few names of frames so that we can understand what we're moving. We generally want to be moving the panda hand, and the name of that is hand frame. Now we're going to set some properties on the overall robot. So the group will be the arm group name, the panda arm will be the overall group, the EEF or end effector will be the panda hand, and the IK frame will be the hand frame. Meaning when you solve for the joint angles for the robot, do it as if the pose is specified for the panda hand. We can ignore the pragmas, that's just suppressing warnings. Essentially, we're creating a pointer which we'll use later. So what we're going to do is start from the beginning of the diagram. So from our current pose generation onwards. Essentially, all we do is create an MTC stage for current state and call it current. So that's what the name of the stage will be. We also are going to save this as a pointer, because there's a part that I didn't mention in my diagram, which is that in order to do inverse kinematics correctly, it needs to have some extra information. So we get the current state, we save it in the pointer that we defined here, so that we can later give it to the inverse kinematics so it can resolve properly. That's our first stage. We're also going to create a couple of planners, including a Cartesian planner. So the sampling planner is our most complicated planner. It's able to do more interesting curved motions. We want to use it for moving the arm around. The interpolation planner is a much simpler planner from between 2 points. Just take snapshots in between those 2 points. So it's not the most efficient planner, which is why we're using it for opening and closing the gripper. It will plan faster because we don't need the complex motion of the sampling planner. And the third planner is the Cartesian planner. Now we want this to move in a straight line between 2 points, because once we've approached the object, we want to move in a straight line towards the object. So for that, we'll use the Cartesian planner. It's one of the advantages of MoveIt that you can have different planners to plan different motion types as you need. So our next step is to create an open hand. So we're going to use the interpolation planner for that, meaning from where we are, open the gripper up, and we only need the interpolation planner to plan that movement. So move to the open hand stage. We want to do that for the hand group name, and we want the goal to be an open hand. So some parts of the robot are defined, like the home position and the open gripper position. So all we need to do is use a string to define those, so open in this case. Then we're going to add it to the overall task and return it. So that's our task built, and all we have in it so far is from the current pose, open the gripper. We've also got our main function. There's not a lot new here from what we saw in the previous example. So we create our node, we create an executor to run that node, we set up the planning scene and do the task that we've just seen, and then we do our normal shutdown methods at the end. Really, everything that we're doing is inside this create task function. At this stage, we can build the project and see it open the gripper. Now that all of our code is written, we want to try and launch it to try it out, but we can't just run like previously. We want to define a launch file for it. So what we're going to do is create a new folder called launch. Within it, we're going to create a launch file that is called pickplacedemo.launch.py. We'll copy the code in, and we can see that there's a configs builder for the Panda arm. It's building our MTC tutorial node and returning a launch description for that demo. Now we also need to change our CMake lists to copy our new launch file in. So in the install section, I was in the right place already. We can add this new line, install directory launch, alongside our project. Now we'll do a colcon build. Remember to do the mix and debug and change the packages select to MTC tutorial. Otherwise you'll be building just hello MoveIt, which won't include the new package. Now that's done, we need to source the setup.bash again. And now we can launch our MTC tutorial launch file, pickplacedemo.launch.py. Remember to rerun RViz so you've got a clean version. And then we can run this. So now our cylinder appears, and you can see we've got a task which opened the hand up. It started out closed, and now it is open. That's our task complete. We can now start adding stages to this to make this more complex and perform more complex motions. First, we want to add our connector. Now, because we're trying to go to our pick object serial container, we need the connector that goes between the previous stage and the next stage. So we can define it after our stage open hand, and you can see our stage name is move to pick. We're doing it for the ARM group name, and we're using our complicated planner, the sampling planner, meaning that we can do more complex motions with curves and so on. We also want to set a timeout of 5 seconds for our planning, and we're configuring our initialization from our parent stage. Now this is pretty common across a lot of the stages. What happens is we've defined these properties here, and we want to share them across the entire workspace. So we can configure the initialization from that and set any other properties at the same time. Once we've defined the move to pick connect stage, we can add it to the task. Now notice we can construct this task without having defined the next stage. That's because although data is flowing upwards, we don't need to define it in the same order. MoveIt will link the data in the order it needs to flow in order to work. So we don't need to say move to pick needs a pose from stage open hand. Instead, we just define one stage, then the other, and let MoveIt define how that data is moved around. Next, we're going to create another pointer. And just like we had for the current state pointer, this one is going to be for the attach object stage, and we'll need it later when we're doing the placing of an object. Next, we're going to use C++'s curly brackets to enclose this in its own scope. So that means if we create a variable like grasp, we can use it within the curly brackets, but not once we leave the curly brackets. So if we try and use it here, that's illegal. If we try and use it here, that's legal. And do make use of this because it will help you organize the code into the scopes that it needs to be, so that you can't, so that you don't use the same variable name multiple times, which I did when I coded this and got strange behavior not working correctly and errors appearing in the log. And it's because I didn't correctly clean up my variable name. So if you look at the tutorial, it will have an open brace, meaning put an open brace in, and if it doesn't have a closed brace, that means the next code will go next to it inside this area here. So with our serial container to pick up an object, we want to make sure that our serial container gets properties from the parent task so that it can access all three of the properties that we've defined. We also want to do our standard configuration. So this says make these properties available, and this says configure those properties. Now that we've got the grasp set up, we want to add our first stage to it, which will be the approach pose. This stage that we've copied in is called approach object. It uses the Cartesian planner because it's doing a straight line motion from the approach to the grasp. This line helps with the visualization by setting the marker namespace, and this specifies that it's in the hand frame. So this is move relative in the hand frame. Again, it does its initialization, so I'm going to skip any mention of initialization because it's pretty similar. And it can also set a min-max distance. So make sure the approach pose is between 10 and 15 centimeters away from the grasp pose. Then we also want to set the direction that we're moving relative in. So we want to move in the Z direction in the hand frame. Then we can insert it into the grasp. So by inserting into the grasp, we're inserting into the container rather than the overall. Now, because we close the brace here, our stage gets cleaned up immediately, and it's already been added to the grasp, so we don't need to worry about that. So we can move on to the next stage, which is to generate the grasp pose. Again, we configure in it, we do our marker namespace, and our pre-grasp pose is open, meaning we expect the gripper to be open before we perform this action. We're going to generate grasps around the object called object. There's going to be an angle delta of pi/12. And our monitored stage is current state pointer, and that helps us do our inverse kinematics. Now, this grasp transform is again needed for inverse kinematics to work correctly. So we're just defining a transformation matrix from the grasp pose. So we're moving 10 centimeters back. We're then going to define our wrapper stage around the generate grasp pose. So it's going to be called grasp pose IK. It's going to set some parameters like how many solutions it wants to be able to create and do its initialization. Also needs to set the IK frame. So we're doing it using this transformation matrix around the hand frame. Then we're going to insert the grasp. Now note that the wrapper actually uses the stage we've just defined, so it wraps around it. So only the wrapper gets inserted into the overall grasp. This is our simple housekeeping stage. All it does is allow collisions for the object. So it gets the joint model group, gets the link model names, and then sets it to true. Our next stage is to close the hand, and similar to our open hand at the start, all we're doing is going to close hand with the interpolation planner. This is our other housekeeping stage, which is again a modify planning scene. We're going to attach the object called object to our hand frame. So MoveIt knows that if the hand frame moves, then the object moves with it. And you can see here that although we're using the same variable name of stage, it's not polluted because it's wrapped in a scope. So here, stage doesn't exist. And our last stage in the pick process is to lift the object up. So all we're doing is from the current position, we're going to lift up 10 to 30 centimeters. Again, that's a Cartesian planner to lift directly upwards, and it's going to be in the world frame, meaning not the Z direction of the gripper, but the Z direction of the world. Finally, now that we've got our grasp completely defined, we can add it to the overall task. And that's our pick stage complete. The rest of it is very similar in order to define the place stages. So I'm going to skip over and come back if there's anything worth mentioning. One interesting point is that the place pose, when it's putting the object back down, is a generate place pose stage. So it's a special kind of stage. It's got the object set to it. And it also has a target pose for the object to be placed down in. So we could, if we wanted, flip this by changing the orientation. We could try and place it upside down. We're also using the attach object stage that we saved earlier when attaching the object as a monitored stage so that the IK can work correctly. So with that, we've created a serial container to place the object. We've generated the place pose, then opened the hand, forbade the collisions because we had to enable collisions. Now we're disabling them again. And then detach the object from the gripper. Finally, we retreated away from the object so that we've cleared enough distance that we can move without worrying about hitting it again. We inserted that overall place subtask into the task, and then we had one final stage, which is to move home. Now, I thought that there was a connector needed between the return home and the place pose. That's actually not true. You can just use the propagator as it is. And that's the task completely defined, our full motion from current position to pick to place to home again. Let's see it in action by building and running. Now we can reset MoveIt to its first position and launch our pick place demo. Our cylinders generated in the world and our demo task is available. Now you can see it's starting to produce solutions as it plans paths, and we can execute one of these. So feel free to follow this tutorial for yourself or directly use the resultant code that is available from the tutorial site and see if you can get to the point that I did, writing the code yourself with only the tutorial as a guide, not copying and pasting. If you're looking to learn MoveIt, the official tutorials are a great place to start. While running through them, we saw how to visualize a robot, how to plan simple motions and more complex ones using the MoveIt Task Constructor, and how to plan motions that avoid collisions. We also went more in depth into the concepts of tasks and stages used for the MoveIt Task Constructor. Now it's up to you. If you feel like you've learned more about MoveIt from this tutorial, my challenge to you is to build a 3D enclosure using a design software like Blender and import it into MoveIt, checking that you can plan motions with a robot arm that avoid the enclosure. This is a really important use case of MoveIt, and it emulates how you might use MoveIt in real life, and how I've used it once in the past. Good luck with the challenge if you do choose to attempt it, and I'll see you in the next video.